Okay, I think we can get started. So it's great to have Alex today. Alex is a postdoc researcher at the Institute of AI in Healthcare and Medicine at Technical University of Munich. His research focuses on the interaction between privacy-preserving methods and the training of AI models for medical applications. So Alex investigates privacy attacks on medical AI systems, as well as the practical challenges posed by the use of differential privacy as the gold standard privacy protection. Um, this is a topic which is, of course, like very near and dear to all of us and MONAI, and especially MONAI Health FL working group. So it's great to have you, Alex, and looking forward to the discussion.
Yeah, thank you very much. Thanks so much for the invitation. There are two things I would like to say before I start off. So first of all, I would like to also introduce my colleague Dima, who's also in the audience and will join the discussion afterwards. And secondly, fun fact, I will present 3 research papers today of mine, and all of them, Holger, you were a reviewer there. So you basically enabled my PhD.
Yeah, right. Very great work. I've been following you for many years, I guess.
Let me just briefly share my screen. All right, can you see my screen?
Yes.
Perfect. All right, I know that I will give some background now where a lot of you will be familiar with. I will do so anyway, just that we're all on the same page. Yeah, sorry for talking about something you might be familiar with already. So first of all, I would like to start off, why do we do this? So AI has enabled us to do very cool things for medical applications. So we saw that we can create very fine-grained segmentations in CT scans, for example, or we can create atlases which are conditioned on a fetal brain age. We can upscale blurry or low resolution sensor data to these very nicely looking MRI images, or we can also find previously unknown biomarkers in unstructured data in an unsupervised fashion. But all of these approaches have one thing in common, which is that they're reliant on the use of medical data. And medical data is, in almost all legislations over the world, considered as a very sensitive type of data. So the immediate question that arises is, if we use this data to feed it to the AI model, can it also be extracted and again? And if you think that this would not be possible, then you would be wrong. There's a large body of literature showing that exactly this is possible. And I would like to especially mention here the top 2 papers, which you see here, called Robbing the Fat and Privacy Backdoors, where Robbing the Fat showed for a federated learning scenario that they can reconstruct almost all input images perfectly with some slight modifications to the architectures. And Privacy Backdoors is even more concerning because they showed that only slight modifications before and after the training, they can reconstruct all the data. I really like this paper, so let me just briefly explain what they're doing there. So basically the scenario that they assume is that there is an adversary who can tamper with an AI model. And what they want to do basically is that they want to enable reconstructions after training, but at the same time, they want to conceal this as much as possible. So they build in some traps there. Then they publish this model and tell you this is the best model that's out there. You should really use it. And of course, you want to use the state-of-the-art model. So you download this model and train your data on your data with this model. And now if you release this model again, for example, you give it to a collaborator, you upload it to your research, or you just make it available to the community, and the adversary gets access to it again, they can extract this data again. And it's very important to know that this is almost impossible to detect. The performance is almost not affected, so you will probably not notice a performance degradation here, and private data can be restored almost perfectly. So this is from their paper on CIFAR 10 data. So you can already see that this is very impressive. And now coming to medical data, this can be very problematic. Here you see 2 mammography images where the upper patient has had a breast removal surgery, probably because of a tumor, and the lower patient has breast implants. So these are probably considered very sensitive attributes here. But we could show, or actually Dima showed here, that we can reconstruct these images here and see these attributes again. So this is very problematic. Now we want to have some techniques which defend against these, and the field which enables us to do so are privacy-enhancing technologies, or in short, PETs. So the first one I probably don't need to introduce to you guys because that's federated learning. You all know about it. Instead of centralizing the data, we send the model around and train on the local sites. So what we gain here is that we have data governance, or retain data governance on the local sites, and do not give up control about the data. The second important technique is encryption. So we want that people who are authorized can read the data, but others who are not cannot read the data. So we just give them a key and encrypt the data. You can sort of picture this as a switch where if you turn it on, you can read the data. If you turn it off, you can't read the data. I will come back to this in a second, why I mentioned this. Now, if you have both of these techniques, you're already in a pretty good state. But I want to point out that model weights and gradients still contain all the information. So if these are released to someone who wants to infer information about the data, they can still extract some information there. This can, for example, happen if the model is released after training, or if participants in your federated learning scheme want to know what the other sites are contributing. So we need another technique, and this is a differential privacy. So what we want to do here is that we want to have information flowing from the data to the AI model, but we don't want to have identity revealing information in there. And now differential privacy enables us to have the sort of a dimmer where we can regulate between very low information and very high information, or very high privacy and very low privacy. I want to just give some key facts about differential privacy for those who are not so familiar with it. So first of all, differential privacy gives you a mathematical guarantee. And this guarantee is that the probability that the output of 2 data sets which differ in exactly 1 entry to distinguish them is limited. So this corresponds very closely to the notion of a membership inference attack. What we see already is that if you use differential privacy, you already have a guarantee that the success of a membership inference attack is upper bounded. Secondly, differential privacy has this notion of a privacy budget. So this is basically your dimmer, where you can set your output to be either very private or very non-private. And now you could say, why don't we just set it to very private all the time? And this is because we usually have a trade-off between privacy and performance here. So the more private you set it, usually the worse your model performs. And lastly, I want to point out that differential privacy is always based on randomization. So there will be no deterministic algorithm that fulfills the requirements by differential privacy. Now, let's make this a bit more concrete. I could now ask you if you smoke marijuana. I will not do that now, but just like imagine I would do that. You would probably feel like that this is a very weird question to ask. And that's probably because you feel it's sensitive information for this round that we have here. But now if we want to do a study on how many people in the MONAI Federated Learning Working Group smoke marijuana, we would have a large error because you probably all answer no. And what we want to do here is now to use a technique called randomized response. So we basically give you a coin and you flip the coin. And if it shows heads, you answer truthfully. But if it shows tails, then you flip it a second time and give the answer which it tells you to. All right. So by that, you can always blame the coin on the answer that you give. So we have this concept of a plausible deniability. Now, of course, if we train an AI model, we cannot ask the AI model to flip a coin, but instead we can add noise to the gradients. And so what we have then is that we get a distribution over the gradient. And now if we train this on a data set, and the data set which differs in exactly one entry, then we get two distributions over the gradient, which are slightly shifted. And now an adversary would get an output here, and they would need to decide if it comes from the purple or from the green distribution here. And the only thing that they could do is that they decide on a cutoff threshold and classify everything to the left as purple and everything to the right as green. So, and you can already see in these distributions that there is a high probability that the classification of the adversary would be wrong. Now, so much for the background. So my research is mainly focused around investigating the practical use of PATS. And I want to present 3 papers here that we did. The first is already a few years old, but I think it shows very, very nicely how such a workflow could look like. So what we asked ourselves back then is, do PATS really fit into a medical AI workflow? At the time, no one really knew, no one really tried. So at the time, the examples all stopped at CIFAR-10. So what we wanted to know is if this is really scalable, how the performance would be affected, and which challenges might occur. So what we built here was a system where we trained in a federated fashion on 3 sites. We sent the AI model to the sites, trained with differential privacy on there, and then aggregated the models using secure multi-party computation. Now, coming back to this example, what we get is a mathematical guarantee that the input image cannot be reconstructed anymore. When we look at the performance, we see that the performance slightly drops when we compare a fully privacy-preserving pipeline in the middle here to a centralized workflow on the left or a federated-only workflow in the middle. But at the same time, when we compare to 2 expert radiologists, our model still outperforms them. It's also interesting to note that if you train your model only on the local hospital sites, then you will get models which perform way worse than our privacy-preserving pipeline here. So you really profit if your pipeline enables you the access to larger wealth of data. All right, so our main findings here were that PATS and AI in medicine are compatible. The data is protected, but there are some effects on efficiency and utility that should be considered. Now, I want to come to a more recent paper of ours from last year. So I already told you, like, we always have this trade-off between privacy and performance for training AI models. And now the interesting thing is that all these papers that use DP, I don't know about any paper that actually substantiated why they use a certain privacy budget. All of them use an epsilon between 1 and 10, and no one really argues why they're doing that. And if you ask a bit closer, you see that this comes from all the literature where they base this off on worst case membership inference attack protection. And I want to go into a bit more detail here why this might not be optimal. So what is a membership inference attack? Membership inference attack, we have a scenario where we have an adversary and an AI model and a data set that's trained on. Then this adversary wants to decide if a certain sample was used in the AI training or not. So they want to have a binary decision if it's the upper or the lower data set. So basically what they extract is 1 bit of information about the training data set. At the same time, they know everything about the data set. They know all the samples, including the data sample that is is or is not included. They know the architecture, all weights, and everything. So it's a very simple setting for the adversary. Now, in many cases, this can be privacy critical because, if you have a council data set, you probably don't want someone to know if you were included or not. But in many cases, this is also not very privacy relevant. On the other hand, reconstruction attacks where the entire input image is reconstructed are always privacy critical as soon as the data is privacy irrelevant. So because they always aim to reconstruct the full information that goes in there. So these are basically the opposite ends of the spectrum. Now, again, you could formulate a worst case reconstruction attack here, which means that the adversary does not need to decide if someone was included or not, but instead you need to decide which of the data samples in the input data set led to the output that the adversary got. Again, this is a very hypothetical scenario. It has some advantages. So most importantly, you can get a theoretical guarantee, which is for the worst case. So you will not have any worse results afterwards. But in practice, this is not very relevant. So what we asked ourselves is, what if we remove the knowledge about the data of the adversary, and the adversary only gets the AI model? I want to point out that this is still a very powerful attack. So the adversary can do with the AI model whatever they want. They can do any manipulation with it, and at the same time, they can observe all intermediate gradients. So our main question here was, what is necessary to prevent these real-world reconstruction attacks? And real-world really means this is still very powerful. And how would this affect the model performance if we tune the privacy budget to these attacks? So first of all, we can calculate the theoretical probabilities of a worst-case reconstruction attack to be successful. On the left, you see a rather large data set. In the middle, medium data set of 10,000 samples. And on the right, you see a very small data set of 120 samples. You can already see that the curve is growing here very fast with an increasing epsilon. Now, if you remove a very slight assumption, namely that the adversary knows the data sample they want to reconstruct, then this curve already becomes much slower. And now if you come to our real-world attack, we see that without any privacy protection, we can reconstruct every single image perfectly. But with DP, first of all, with a privacy budget which is tuned to this worst-case membership inference attack protection, we cannot reconstruct anything. This is not surprising because this protects against a much harder attack. But now the question is, how much can we increase our privacy budget? And it turned out that for our setting in this data set, we could increase the epsilon to an insanely high number of 10 to the 12. And only at 10 to the 15, some images were able to be reconstructed. Now, when we look at the performance, how this performs the utility, we see that for a rather large data set, the difference is actually not that drastic. So you can, on this data set, on Red ImageNet, you can train models which perform still very well with very conservative privacy budgets. But with our large privacy budget, you're on par with the non-private model. Now, if you go to a small data set where we segmented the tumor in the MSD liver data set, we see that these small, very restrictive privacy budgets prevent the AI model from learning the task almost entirely, and only our compromise between privacy and utility here enables us to be on par with the non-private model again. So what we found here is that even large privacy budgets provide a certain protection, and also I want to point out here that these large privacy budgets usually imply that you have negligible performance losses. So this might be a very good compromise if you cannot sacrifice any performance, but you still want to have some protection. It's not a perfect protection, it's not a theoretical guarantee anymore, but in many cases, this will suffice to prevent very strong attacks. All right. And the last paper that I want to show you is where we looked at how does differential privacy interact with fairness between demographic subgroups. So what we had here were two data sets, a chest X-ray data set and a pancreatic tumor data set. And for both of them, we had the diagnosis as well as the age and the sex of the patient. So we trained on diagnosis, and then we stratified for the age and the sex and looked how different subgroups were affected. So let's look at the sex first. So you see in the dashed lines, you see the non-private performance here. So what we see is that female patients are classified slightly better than male patients. And this translates to the private performance. And what you can maybe already see here, it's very slight, this effect here is that the more private it gets, the larger this discrepancy is between these groups. It's more pronounced for the age. So again, what we see here in the dashed lines is non-private performance. Young patients are classified quite a bit better than old patients. I want to point out that young patients are completely underrepresented in this data set. So we had about 4,000 young patients here, but we had about 60,000 old patients. So these are completely overrepresented. So it's not about representation here. And again, this gap translates to the private performance. So what we see here is that, again, the more private we get, the larger the discrepancy is. So what we found here is that privilege and discrimination are amplified by DP. And it's not so much about the demographic representation, but in our case, it was more about the diagnosis difficulty. All right. I would like to give a brief outlook, what I think is our relevant questions for the field. So I classified this into two categories, open questions and future research. So first, for the open questions, I think what is a very interesting topic, and no one has really answered that. And also, I think it's not possible to answer this from a technical perspective. This is more of a legal and societal perspective. It's what is a good way to decide upon a privacy budget. So no one right now actually knows how to set your privacy budget. I think what you would need here is guidelines to say, like, for a specific attack in a specific scenario, you will want at most a certain risk. But yeah, right now this doesn't really exist, and everyone just wants to have zero risk. But this is not possible whenever you use data in a meaningful way. Also, what DP could enable in the future is that data could become a consumable good. This is because you have this privacy budget. So if you train with a privacy budget, you're expanding it. And once you expanded it, you cannot use the data anymore without allocating more privacy budget to it. So your data actually is wasted if you want. So you need to decide who you give it to, how you allocate your privacy budget, or if you even sell privacy budget. Now, for research, I think there are three directions which are really interesting here. First of all, I think there will be technical solutions which improve the privacy utility trade-off. I want to mention here the developments around DP follow the regularist leader, which seem to be very promising, but they have not shown yet on a larger data set as far as I'm aware. Then, of course, I think a very big topic will be private LLM training. LLM training and differential privacy are not natively compatible. This is mostly because DP assumes a notion of individuality in the training data. So you can say the first image belongs to patient A and the second image belongs to patient B. But in text data, this is often not the case. And then thirdly, I think what's the holy grail here of differential privacy is DP synthetic data. So I think this is really important because if you can solve this challenge, then you can create synthetic data based on your data set and can train all subsequent AI models and never need to expend any privacy budget anymore, and keep your protection there. So yeah, I think this already works for some tabular data sets, but I think no one really has a good approach for image data sets yet. All right. So let's summarize. I think there are three main takeaways that I would like to give you. So first of all, I think paths are an important tool to provide data privacy for AI training. Probably not very surprising to you. Secondly, I think you need to consider the effects that it has on efficiency, utility, and fairness. They're all manageable, but you should be aware of them. And lastly, I think a pinch of privacy is always better than no privacy. It's because you need to find a compromise between privacy and performance here. And with that, I would like to thank you. You can reach out to me if you're interested in more of my work or in a collaboration. And thank you very much. I'm happy to take any questions.
Thanks so much, Alex. That was a great talk. Does anyone have any questions? You can either raise your hand or just feel free to unmute yourself as well. I actually have I'm curious about the reconstruction attack. How was it implemented?
You're asking about the where we evaluated the privacy utility trade-off?
Right, exactly.
Yeah. So this is actually the rubbing the fat paper that we re-implemented here. So
right.
what they are basically doing is that they're inserting a linear layer in front of the network.
That makes sense. Yeah, I can't remember the name of the paper now, but there was a paper a couple of years ago which was able to prove that reconstruction is much harder than membership inference, and that if you only want to protect against reconstruction, you need a much larger epsilon.
Yes,
do you know the paper I'm referring to?
I'm not actually sure which one it is, but yeah, it makes a lot of sense from an information perspective, because membership inference attack is always one bit of information, while a reconstruction attack is always the full information in there. So like for an image as a very high dimensional data, this can be some megabytes.
Yeah, exactly. I think that was exactly the intuition they used and formalized it essentially. And the claims will match your observations. I think that. Oh, go ahead, Dima. See your hand raised.
Yeah, I think I know one of the, or like two of the papers you're talking about. So one is RERO, the reconstruction robustness, where they try to reformulate the privacy as the not a general, privacy and information release problem, but the problem of being able to defend yourself provably against reconstruction attacks specifically. So that's a RERO paper. And there was one from Shokri last year.
I think that was one I was referring to.
Yeah, the leave one out distinguishability, I think it was called. Yeah. They essentially try to frame, they try to do it the other way around. They try to frame, is membership inference in any way the same as reconstruction? And to some extent it is, if you treat this problem as leaving each individual out of the data set and performing the reconstruction, etc., etc. So these are essentially not like your epsilon scores. These are some other metrics derived from epsilon, which are more understandable in the specific context you're operating in. So because people are mostly scared of reconstruction attacks because I just came back from ACM law, and all people could care about was, deduplicating the data set, making sure the diffusion models don't produce copyrighted content. And essentially every discussion that was happening was, does the model produce the content that it shouldn't be producing? Or in case of Alex's work, does the model memorize enough information for someone to extract the original content? And this is the thing which is on everyone's minds these days, not really membership inference. So, they're not as strong as DP when it comes to protection, but they're much more, put into the reality of things. I'll link the papers in the chat, by the way, because I have them open somewhere across my 25 tabs.
Amazing. Any other questions from the group?
Yeah, these reconstruction attacks you looked into, they're basically based on the updates in a federated learning scenario, right? So you're considering a malicious server who's reconstructing the data from clients, right?
Yes, in this case, it is based on a federated scenario where we have an intermediate gradient. So yeah, as I said, like it's still a very powerful assumption that you take here. But at the same time, so I think this transfers quite directly to the privacy backdoors paper that I showed in the beginning, because it's based on the same principle. So you don't necessarily need a federated setup. It can also happen if your adversary is able to tamper your model before the training.
Okay, because yeah, I'm kind of raising this because I think that with some of the cryptographic techniques and hardware-based trusted execution environments, we can probably make the federated learning setup secure, right? So let's say the server is trusted, and we can actually ensure that it cannot be tampered with. So there's no malicious actor that has access to the server and can observe individual updates coming from the clients.
Yes, this is the discussion that's always revolving around differential privacy. Do you actually need it if you can ensure that no one gets access to it who's malicious?
Exactly.
You don't. Like, if you can really ensure that, if you have only trusted participants and no one tries to infer anything about the data, you don't need it. The thing is, as soon as you release your model, or you give someone inference access, or you give someone access to your federated participants who can infer something about the gradients, you are vulnerable.
Yeah, so I was wondering if you kind of looked into this, like what happens at inference time, right? The trained model that comes out of federation actually doesn't even need to be federated learning, right? As you say, it could be just any model that you train. You might want to open it up for inference API, or even open source the model, right?
Yeah.
What are the risks in that scenario, and how can we quantify?
So I mean, obviously, the less capabilities the attacker has, the harder it gets for them. I think in this case, we actively chose a very strong attack, because we wanted to show that even if you have a very strong attack, which is still quite unrealistic, you can already use this much higher privacy budget.
Right. I guess that's good news.
I hope so too, yeah.
Yeah. I mean, if somebody else has questions, please go ahead.
Yeah, a quick comment on your point, Holger. I think there was I remember a paper a while ago which was trying to examine the privacy leakage of the end model, of the finally trained model. And there was some evidence that training it in a centralized way is less private than training in a federated way, even if you only care about the end model. So there's something about the federated learning training process seems to reduce the privacy leakage even of the end model. I don't know if there's been much follow-up work on that paper, but yeah, that was an interesting observation. I'm more curious about what how do you see this definitions of DP translating well into the medical space? Like, I'm curious about how, if you have had conversations with folk in medical imaging or medical AI in general, and what is the notions of privacy folk in the space care about, and how does that map or doesn't map to DP?
Yeah. So, I mean, I already mentioned this. No one really has this notion what is now a good privacy budget to choose. So this is a completely open question. We went with this question to the data protection officer here at our hospital, and they basically told us, look, you can do whatever you want, but if it goes wrong, you're at fault. So yeah, I think like no one can really answer this there. If you go more into the technical perspective, I think so membership inference attacks and reconstruction attacks, they're both, the one is heavily underestimating the risk, the other is heavily overestimating the risk. I think the interesting thing is actually singling out attacks or attribute inference attacks. But these are very hard to describe in a mathematical way. And they're also very much dependent on the data set you have at hand. So I think like if you really want to quantify an important risk, it's a singling out risk, but it's very, very hard to do this in a general way.
So I didn't catch what you said. What risk was that?
Singling out, it's called.
Singling out.
So
I see.
yeah, singling out a patient so you can identify them in a data set.
I see. So the real risks, say the protection of data protection officers care about, are really these attribution inference and the singling out.
Yes, because that basically allows you to identify the patient. So you can basically say this was now patient A who was at this hospital. And this is probably a legal nightmare for any data protection officer.
Yeah.
What's your experience with? Oh, sorry. Go ahead.
No, go ahead.
I was just wondering if you have some experience with regard to like different types of data, like where do people think in medical imaging in particular, like which data modalities are more concerning regarding to identification of patients?
I think so. I'm currently working on a study where I try to evaluate that if I can, from anonymous medical data, re-identify patients. I'm not so sure about the different modalities. I think the most obvious one are face CTs or MRIs, where you can reconstruct the face, or so head CTs. But I mean, they're invented the skull scraping, and like I think this is a very easy way to achieve protection against the most obvious attack. But then again, like I think there are so many features in your body which are unique, which you can link back to a patient. Like you can, I mean, we have so good classifiers and AI models, they can probably tell you anything about CT scan if you just train it on enough data with the right attributes. I probably think like the more information that is in there, the easier it is. So I think MR scans and CT scans are easier than X-rays. But at the end, like even in X-rays, there's so much information that I'm pretty sure, like for even large data sets, you can link them back to patients if you just have the data to train it on.
Interesting.
Yeah, and there was some work which showed that just from a CT scan you can infer age, race, and ethnicity of age and ethnicity of a patient, right? And of course, gender.
Yeah, I think this even works on X-rays, which is crazy to me.
Okay, maybe another topic we should talk about is what would it take to bring some of these like best practices into MONAI, right? As far as I'm aware of, there's no examples now of differential privacy being used in the MONAI repository. I could see like it would be pretty nice to have a tutorial, right, or something like that, where we show that maybe you can take some of the state-of-the-art techniques at least and apply them to models that are typically trained in medical imaging.
Actually, I can really recommend to use Opacus there. Like by now it's a very good framework, and it should be very easy to integrate into any PyTorch code that you have. I'm assuming you're using PyTorch. So yeah, so if you use Opacus, they have very good tutorials and should be very easily transferable to your repositories.
Yeah, is this something you would be interested in collaborating on?
I can certainly,
yeah,
I can certainly give you some guidance there. We have a lot of experience here. I probably won't have the time to implement it myself though.
Can you put the link to the framework you're talking about in the chat? Is it Opacus
yeah, sure.
or?
Yeah, it's Opacus, right?
Yeah, I'm also curious about another. I think another. So of course, like Opacus kind of libraries for making the training private are really useful. But maybe more practical, given that TP is not something which is yet widely used in the medical AI community. Maybe important first step would be just testing existing models, right? Like, can we implement some of these attacks which you've found on these existing models? Say, can we perform some reconstruction attacks or inference attacks on the models in the current MONAI library?
I think there's the repo from Jonas Geiping, right? Which I don't know if you use that directly to implement some of these things.
Yes, I did. Like it's a very good repository.
Right.
Yeah. And I mean, like for all of these approaches that assume a malicious adversary, if you don't use DP, you can basically already assume that you have 100% reconstruction performance.
Wow.
Do you remember what? I haven't looked into it for some time. What was the name of that repo?
Timo already put it into
the chat already, yeah.
Reaching, right? Okay, yeah. So yeah, Bernie, that could be also a nice thing to have, especially. I think like MONAI is mostly concerned about the centralized training of models, right? But if you can do some kind of model inversion attacks, as an example, it would be really cool.
Yeah, I think it would also raise the awareness. I think a lot of people in the medical community are not aware that this is actually possible. Like, I think you guys really have the community to make this publicly known.
Yeah. It would be cool. Okay, any more questions?
I'm curious if you guys have also been thinking about private. You didn't mention, I think, a bit about privacy in the generative models and say text. Do you see how do these notions of DP are not necessarily defined for those modalities, right? Like for text and so on. Do you have thoughts on what we can do or how we can translate these?
I mean, what all the big tech companies are doing is they're just hoping it doesn't go wrong and don't give you a white box access. So that's something you can do, which makes it harder. But I think there is no guarantee. And I mean, you already saw like how many jailbreaks that were out there on these very famous models. Yeah, I think like a mathematical guarantee has its advantages, definitely. At the same time, I do not see a straightforward way to combine DP and LLMs. Maybe you can do it in a very specific medical scenario where you have patient reports, and you know that this text is only about this patient, then this probably works quite well. But if you just use the entire internet to train on, you will not be able to use DP. So yeah, I'm not sure what the answer will be. I think like this is an active research direction, and probably Google, Meta, and all of the big tech companies are all researching that right now.
Yeah,
I'm actually
like,
surprised that that LLMs haven't leaked any social security numbers, or none of these large models, Gemini and is
they
that?
have.
I've seen something long. Maybe a few months ago, but it's surprisingly, like, at least it's not a daily occurrence, or it's not something. It's not something as prevalent as I was hoping it to be, but I don't know. Well, maybe they're doing something right.
Yeah, I think there are two reasons for that. Firstly, they have like tons of training data, so like a social security number is probably not directly memorized. And secondly, they also invest a lot of time to prevent this by just checking a lot of outputs. Yeah, but they will not have any guarantee that it's not happening. And that's why it's happening sometimes.
Okay.
There are manuals. They're basically scripts which are used to remove these sensitive data sets during the training. Basically, whenever it detects presence of these sensitive data sets, it just drops it off from the training. And also during generation, there's loads of filters on after the LLM generates an output to stop these from. But yeah, it's still possible to circumvent all of these, and but probably not for everyday users. But there's definitely papers which attack these systems.
Yeah, and I think this is also a very, very fun research direction to attack these models.
Do you see any of these being relevant to the medical AI community, or say in these vision language models which are used for medical imaging and so on?
You mean LLMs?
These kind of privacy attacks and
well, I haven't seen one being actually executed, but I think at the same time, for many setups, it would be quite trivial. So I think a lot of people are just not aware of it. I think we should be very careful here, because I think there will be a huge scandal if it gets publicly known that some adversary were able to reconstruct malicious data from AI models. And I don't think we want to risk that. Like, for that, I think AI is too valuable for medical tasks. So we should be really careful here to not give up like the reputation in society. So yeah, no, I've not seen it yet, but I'm expecting the worst.
yeah, any other questions from the group?
Actually, I had another kind of question. Do you think there's some data, like if you think about the whole data set, right? Are there some data points that are of higher risk of being leaked? I'm thinking like, is it typically, does an LLM memorize the outliers more than something that is living at a kind of the mean of the distribution?
Yes.
Yes,
Yes, exactly. That's the case. Like, outliers have a much higher risk. Like, actually, a colleague of mine just sent a manuscript out for review where he showed that in chest X-rays, ethnic minorities have a much higher risk of membership inference attacks being successfully performed. because they're completely underrepresented in this data set. So yes, like the risk is very different for patients and or data samples, and the rarer they are, the more valuable they are, the more they get memorized, and the higher the reconstruction risks and membership inference attack risks become.
Yeah, that's concerning.
Yeah, it is
But
very
yeah,
much
something people need to be aware of, right? Yeah.
Yeah.
So that's really cool. Yeah, if you can share that paper's out already, or in the works?
I don't think so. Yeah, I think he will probably put it on archive at some point, but I'm not sure if he's already willing to do so.
Okay. Okay.
I will ask him.
Yeah, let us know.
Yes, I will. All right. Any more questions?
So it's been very useful, very, very useful conversation.
Yeah, thanks very much.
Thank you.
Thanks so much, Alex.
Thank you for the invitation. I was happy to be here.
Great. Thanks. Good to see you guys. Bye.
Bye-bye.